Tells me he has a background shared in both meteorology and CFD, and he's going to talk to us about some CFD ideas. And he's here until the end of next week.
Thank you. So I don't think we need the room to be so bright. Okay, thank you very much. First of all, I'd like to thank organizers to invite me to be here to share some of our recent work with you. I just try to pick up some important points that I think you may be interested in. Basically, today's talk will mainly on the CFD aspect. The application of this method to the atmospheric modeling will be presented by Dr. Chen next week. I will in the last slide I will make a brief advertisement about that. So what we are going to talk about is to use multi-moment. I will explain in a second what it is in our context. To construct high-order finite volume method to solve a fluid dynamic problem. This is a cooperation between me and my PhD student. They made a substantial contribution to this work. So this method is actually a kind of high-order scheme with a local reconstruction. So why we need local reconstruction? So this is what we can expect from this kind of method. The first one is adaptivity. Okay. Otherwise, you can use Wayno, which works pretty well for almost all of CFD applications. And another one is that if you use some kind of reconstruction, you can get a kind of a spectral convergence, which is very attractive. And I just give an incomplete list here for existing work. Spectral element method, you know very well, and DG, which probably is the most popular method now used in a computational mechanic community. And there's still some other variants very close to the spectral element method, like spectral collocation method, spectral volume method, or spectral difference method. And in Japan, Professor Yabe devised a very efficient and very basic physically motivated method to solve the advection equation, which he used two kinds of what we in our terminology we call two kinds of moments to update as a semi-Lagrangian solution to get a high accuracy for advection equation. So, inspired by this this idea, in our group, we started this work from about 2002. What we want to do is try to develop a general formulation where you can design your scheme, which is not so mathematically restricted, but can be very flexible, and in some cases it can be even attractive in other aspects. So, to avoid the possible misleading of a multi-moment, the word that I will use, I just want to give a very short explanation of a moment. This is moment in Wikipedia. So it's a surprise to me why people like the moment so much. We can find moments as a word in many fields. Okay, science, engineering, and also here, even in art, music. Actually, I just want to this is a piece of very beautiful melody, and it's called Moment of Sound. Yeah, I believe all of you know this very well, but I have to stop it here and continue to talk. The moment here is just just give you a relatively clear image of what is moment we used here. For a given physical field, we need some discretized quantity to describe the spatial distribution of this quantity. So the way to do that is not necessarily you can choose a test function and do this inner product, and then you can have some discretized quantity. Okay, for example, this is a pointwise moment, the point value, and the derivative at this point value. And also you can have a volume integrated kind of quantity. Here is integrated moment. This is a volume integrated average, and then you can also include some other kind of variations there. So those kind of moments or quantities reflect different aspects of a physical field. They are different quantities, and we need to deal with all of those quantities. Just follow the original definition of those as discretized variable. Okay, this is the outline I would go through for today's presentation. And first, I will talk a very basic idea to use multi-moment to construct a finite volume method. We start from the finite volume method. This is the control volume, and in a conventional finite volume method, we need this volume integrated average like this, define this, and if we want to update a time evolution equation for Q, the physical variable Q, we need to calculate the numerical flux. Okay, so and then we get a balance of the flux, and we can get the time tendency of Q. This is a conventional finite volume method. So in this method, in order to calculate the numerical flux across this boundary, we need to find some formulation which is just based only on this volume average. Okay. So you have many ways to do that, but the only discretized quantity is a volume integrated average. So now, what we want is just the flux, numerical flux across each of these edges. So if we know also some the values at this point, for example, maybe we can make things different, and which many cases will give you a more efficient option. So we add another moment as a point value. A PV is not a potential vorticity in a geophysical fluid. It's just a point value here. So we know these values at this red point. This idea can be extended to actually arbitrary kind of shape, a geometry. If you like, you can define these quantities. In some other case, we can even define the surface integrated average. For example, we have a rectangular here, and we define the average of the physical variable along each edges of its control volume. So this is what we call surface integrated average quantity. Okay, you have three at least quantities, moments. They are different discretized quantities. So next is the key, maybe the only idea. The basic idea of the multi-moment finite volume method is to try to memorize those different kind of quantities or moments and update all of those step by step. Okay, what we can get from this multi-choice or multi-moment formulation. First thing is that we can make the updating process very flexible and very efficient. For example, in this case, we can try to update the point value by semi-Lagrangian approach, which has to be very which has been very popular in meteorological modeling society. We can also use the Eulerian approach. In this case, we just fix the point of solution at this point, and we solve point-wise Riemann problems. And for time updating, we can use a Runge-Carter type of method to do this. So with this point value given, we can calculate the flux, numerical flux, based on this point value. It's just straightforward, okay? And what we need here is that the conservation, the exact numerical conservation for this value, volume integrated average. We do not want those kind of point value to be exactly numerically conserved. So it just gives you different options. Okay, you can try to. You do not need to care about the numerical conservation for this point value. So in many cases, you will get a benefit from that, particularly for the computational efficiency. So this is the basic idea. And the thing here, I will just show you with this concrete example how we do that. This is 1D multi-moment standard volume method, which we can calculate. We can design the scheme up to arbitrary order of accuracy. This is 1D conservation law. We always suppose that it is a hyperbolic type of equation. And we now define the moment to be the point, the value, and also the derivative of a physical variable at these two ends. Okay. And also, because we need this to guarantee the numerical conservation, we need another one. This is a cell integrated average, which is defined over this cell. Now we have to derive some the evolution equations to update each of these moments. This is a pointwise the form of this one. We write it at these 2 points. This k is the order of differential, the derivative with respect to the space. And also this is exactly nothing but the standard volume formulation. Okay, this is the flux, flow in and flow out. So next thing left for us to do is how to calculate this flux function. There are many existing works on this, which we can choose by a different way. For example, some people devised a solution based on analytical work for this kind of generalized Riemann problems where we do not only consider the Goodenough types of piecewise constant solution, but also the variation in space. And more simply, we can also use this approximation, numerical approximation Riemann solver to do this. So it's just very easy, at least for one dimension application. So now we have those quantities given the value of a physics variable at the two ends, the cell, the two boundaries of a cell, and also the derivative, and also the integrated average of it. So we can actually construct a hyperbolical interpolation function. There's another problem, oscillation. Okay, if you use a scheme which is higher than second order, definitely for this jump or discontinuity, you will have oscillation there. So it's very easy for us to introduce a slope limit here, which can effectively work to remove the numerical oscillation. So I will not go for more details about this. I'll just show you some of the 1D work. This is a third order convergence. This is the test for advection quotient. We just calculate a sine wave and see how it converge based on the grid refinement experiment. This is a Euler equation where we have a shock wave and expansion. This is the interaction of two blast waves. It just to show you that this kind of scheme works and is comparable to the state-of-art numerical method. This comparison of another numerical example. Okay. So this is what we call a direct multi-moment formulation, by which we mean that we treat the moments themselves as a computational variable. We update those quantities directly. So it's a kind of choice, but we will, I just list up some reason that we stop here and we shift to another direction. This is the next part of the talk. For this one, direct multi-moment formulation, it works perfect for 1D, as I just show you. And for practical multi-application, we can very easily construct the formulation up to third order accuracy by using, for example, the integrated quantities over the volume, control volume, and over the line, the edges of the control volume and the surface, or something like this. But it is not easy to handle things in multi-D. For example, the differential type of quantities in multi-D to get even higher order scheme. So for this direction, we stop at this stage, and we are looking for another alternative approach. It is the combination of Lagrange and the Hermite type of reconstruction. We compute the solution at the collocation point. Actually, this is kind of a collocation method, as I will show you later. And but we construct the flux function with multi-moment constraint. It is just a Hermite type of interpolation. Okay. So this just lead another type of method. We have two names, whatever. you can call it a multi-moment constraint collocation formulation, or you can just inverse the order, call it a collocation method with multi-moment constraints, whatever the name is. So next, I will just go to this story. But before that, I just want to show you very briefly some of observation we can get for both Lagrangian interpolation and Hermite interpolation. This is a mesh cell, okay, over which we want to construct a polynomial for high order scheme. So one choice is Lagrangian interpolation, which means that we know the values of Q at this red point. So directly we have a Lagrangian interpolation. This is the basis function of Lagrangian interpolation. Okay. But if we are given with some other kind of quantities, for example, this is the average cell average value, and the Q, the point value of a physical variable, and also its derivative with respect to space. We can have another choice for interpolation. So we call it a Hermite interpolation, but maybe it's not canonical, not standard. But anyway, it's kind of that's kind of interpolation. So if we check further what kind of quantity we use here, we can find that in this case we only use a point value. Okay, so we can call this is a single moment method in our context. But for this case, we use not only point value but also the average, integrated average value, and also in some cases the derivative. So we can that means we use a multi-moment of Q for the reconstruction. You can in the same the method is different, and information that you use for reconstruction is also different, but you can get the polynomial function. The polynomial functions are also different in two cases. So this makes story different. Let me just show you how Hermite interpolation converge. So we start with this sine wave indicated by the red line, and we have one quantity which is a cell integrated quantity, and two point values at these two ends. We start with this, and then we increase the derivative. This is first order derivative at two ends, and then increase this is second order derivative, and we get a converged interpolation function. So we check the convergence rate by plot the error against the degrees of freedom we use here. We compare this curve with this picture from a book of Professor Boyd. So we can see we can also get some kind of spectral type of convergence. Or here he used the geometric type of convergence. Okay, so it's reasonable to choose the Hermite type of interpolation for reconstruction. Another problem I'd like to you to see is the Lagrange problem for a Lagrangian type of interpolation. So if you, for example, if you want to fit this red line with a polynomial, and the polynomial is determined by the values that you sampled at equally spaced point over this domain, you will have some trouble like this. Even worse, if you increase the order of a polynomial, this oscillation will be enlarged. Finally, it's not stable. But But if we choose to constrain the polynomial through these two ends from a point value up to different orders of derivative, we have a fitting like this. So if we try to, you may not satisfied with this one, the peak is lower than this one, and maybe you can try that, okay, I use 1 point here, and some other things from two sides with derivative, different order of derivatives. You can have a combination of Lagrangian and polynomial. Okay, so even you can also have some other choice, which gives you a different resulting fitting. So we see the quite different properties for two kinds of interpolation. And now, as I just said, we will try to devise a multi-moment constraint collocation method. At first, I just give a general form of it. We consider this conservation law. F is a flux function, which is a function of Q, and Q is a state variable. And we have this mesh element, and we set a solution point inside this mesh element, where we solve the point value of Q at this point, at this solution point. Okay, we write in a journal form like this. This indicates the value at this solution point, which can be updated by this differential form or strong form of conservation law. And it's very simple and very easy to understand. Another thing is that we can very easily show the conservation of this, even we update the point value pointwisely. So you can take integration with respect to x. You get from this formulation, you get something like this, which means that the weighted value, the point value, is conserved. Okay, this is just a perfect finite volume method, finite volume formulation to do this. And the thing is that we need to make this numerical flux to be continuous at a cell boundary, to be a certain value. The value is need to be calculated from a Riemann solver. Okay, so now I just go with more details about the procedure to devise this types of method. You are given the values at this grid point, this blue point, the solution point. And at first, from this information, you can construct a Lagrange interpolation function like this. Okay, not only for Q, but also for F, the flux function. It's very easy. And you get the interpolation function cell-wisely, which is Fix. But since all of those reconstruction is just isolated for each cell, we do not have information from other cell, from a neighboring cell. Of course, you cannot use this directly for calculate here. You cannot use that one directly here to update the Q. So we needed to do something else. The first, we need to find the flux at the cell boundary, and even in some cases we need to find the derivative of the flux function by solve the Riemann problems at a cell boundary, because we know all of those information from a primary interpolation we just talked about, this kind of f, left side and the right side of those values can be calculated from a primary interpolation function. And then the second step is that because we cannot use the primary interpolation function directly for updating the Q, we need to construct a modified flux function, use available information from those kind of stuff we get from primary Lagrange interpolation. The problem is that we are given more than we need in many cases. So how to choose the constraint conditions to fix this modified flux function? It's a problem. Okay. So let's just show you a different way to do this. The first one is actually a Lagrangian type of formulation. Here we have the primary interpolation function constructed like this. Okay, we do not have values at a boundary point, and now we need to solve a boundary value. We suppose that we have a proper solver, Riemann solver, to do that. And then this in a paper of Dr. Feng, 2007, he suggested a very general formulation to express the modified flux function, and here he introduced a correction function. This correction function can be different, but have to satisfy this kind of conditions to guarantee conservation. Okay, so by properly choosing the correction function here, we can recover exactly the nodal type DG, discontinuous Galerkin, and also a spectral element method, and even other kind of numerical method. This is one choice. We can do this, and we can get DG formulation. Okay, so which is just show that we this pink line is a modified flux function. Okay, use this one, we can back to this equation to update this. So this is one option. Okay, here we can see all of the quantity used here are the point value. This is basically essentially a Lagrangian type of formulation. Another Lagrangian formulation can be done even more efficiently. We just simply use the collocation idea. Okay, we know there is the values as there is 2 points, and we just connect these 2 points with the original values of the primary interpolation function. So again, you can get a modified flux function like this. You have 2 additional constraints, so which gives you maybe k plus 2 order of convergence rate. This is a comparison. You can use DG. You get a solution like this. This is a advection of a square puzzle problem with a constant velocity, and this is a 3-point collocation method without the Galerkin inner product procedure. We can also get a solution. So if you do a Fourier analysis, you will find both have the same convergence rate, almost the same. Okay, this is another way that we use. We use a multi-moment to construct this modified flux function. In the previous two, we only use a point value to do this, which are basically kind of Lagrangian interpolation. Here, we try to use something different. We have to use the value, the flux function, the value of flux function, which must be shared by two neighboring cells to guarantee the numerical convergence, numerical conservation. And we have some other values like this, the value of a flux function, a primary flux function, and inside the cell, and in some cases the derivative of this primary interpolation function. And also, if you like, you can increase the constraints at the two ends of a cell boundary. So, as I said, we have more than what we need. So we have to choose among them. This is one of the choices. Okay, so you can also, by this way, to construct an interpolation function, modified flux reconstruction. This is the general picture for this formulation. You can you have information like this. You can choose different kind of constraint conditions, and finally you get this one. This is a modified flux function that you need to update each solutions at this solution point, the bullet point. You can see from this this slide, you can do things very flexibly. Okay, the solution function can be the constraint points can be different from a solution point, and you do not necessarily to use a point value as a constraint condition. Okay, let me next just show you some examples of schemes along this.
A question before you go on. Can you go back one slide?
Yes.
So this more general one, it seems to me the modal DG would be a special case.
Nodal DG.
The modal.
Modal DG. Yeah.
Should be in this form.
But modal DG use here. Actually, we still use a point value to update to be updated quantity.
Yeah.
Okay, but model they update the coefficient of
Right.
each mode.
But a modal one, I think, might be equivalent to one of these, although the representation is very different. Have you looked at that?
Probably.
Okay.
Okay. Yeah, that can be ideal. Yeah. There should be some connection there. Okay. This is the simplest one. We call it the MCV2. MCV3 scheme. This is third order scheme which has been published in a paper 2009 in Journal of Computational Physics. Here we use this three kind of constraints. We use the value of a flux function and the first order derivative of it at its two sides. So we have four constraint conditions. We can get this interpolation function. Okay, so we know this. So we can do directly to have a value of this modified flux function at the solution point. Okay, like this. So if you just you know f, and this is the first order derivative of f, and which is also a function of c, the space coordinate, and then you just put these values in this interpolation function, you get explicitly formula to update to update this one. So it's very simple. It's very simple. This line just show you the exactly numerical conservation. Okay, you sum up this weighted flux, first order derivative of flux function over this cell bound over this mesh cell, you get exactly the which is net flux, the difference from the flux flowing and the flood. So you can choose another type of solution point, like this. This is a Chebyshev-Gauss point. So you have another formulation like this, but you can also get exact numerical conservation, like this. The weight factor is different. So you can compare the 3-point scheme, the result of this. You found this. This is one which is acceptable. Another thing I want to show you here is maybe it's very interesting, but we have not explored further about this to see how it can be beneficial for real application. But maybe you have an idea. If a scheme can do this, what we can get benefit. It is the location of a solution point is not sensitive. So we test this three cases. The blue one are solution point. Okay, you choose this, and even you can make a solution point like this, and you calculate a Gaussian distribution, advection quotient. After 1,000 steps of calculation, you have a solution like this. So I don't think I'm not sure if it's that useful, but I believe we have in some cases it should be attractive. Okay, let's just show you another one. Another type of constraint. Here, we put constraint calculated from a primary interpolation function at the center point from the value, the first order and second order value. And then this is what we definitely need for numerical conservation. Okay, so this is a constraint condition. Again, we get another reconstruction flux, reconstructed flux function, and we have some similar, but not, details are quite different. But the procedure is just the same. You can get this one to update the three values at this solution point, and again you can also recover exactly the conservation, and you can choose different solution point. The previous one is just for a Chebyshev point. This one is for equal distance solution point.
Why do you have to use the Chebyshev points?
A solution point?
Yeah. Why Chebyshev? Does the integral has a Chebyshev weight? Does the integral has a Chebyshev weight?
Yeah, this is should be something like that. So you just do the integral over with respect to.
The integral doesn't have the Chebyshev weight function. Then, if you are doing a Chebyshev weight, the accuracy we may not get the accuracy.
We do not find that there are that much difference here for accuracy matter. But maybe this is another thing we need to consider further. Okay. I need to go more faster. This is another interesting scheme. Here we set the solution point at the cell ends. Okay, but as you can see from this formulation, the values from right side element are different from left side element, even they are at the same position, at the same location, like this. So that means in this case, we do not need to do interpolation. We just use the value directly as what we need in a Riemann solver. Okay, Fourier analysis is just straightforward. If you use a harmonic wave solution, and for this linear advection equation, where the advection velocity is unity, and you can put this in a scheme, and finally you can have a semi-discretized equation like this. So S is what we call the amplification matrix. We want to see some of its properties. So the eigenvalue spectral of different schemes are given here. This is for a DG. We see, but for all of the schemes we have, we found that the real part of eigenvalues are all negative. That means all of these schemes are stable. But the largest eigenvalue, which is the spectral radius, are different. DG is the largest one, and this is MCB3 is approximately half of DG, which means that we can use a larger CF number, because if we use, for example, the third order Ranjikata method, we have to put the value of spectral radius times delta t to be in this area. So as we have seen some representative, three representative schemes like this. They have also different spectral. This one is the best one, which we have the smallest one. Spectral radius. This is analysis of a truncation error for a 3-point scheme. So you can see lambda 1 is a physical model mode. 2 and 3 are computational or spurious mode. We can see for the computational mode, we have very large values which are negative. That means in all of the schemes, the computational mode will be very quickly dumped out, which will not affect the solution. So we have different orders, different errors for different schemes. But I will not. I don't think I have enough time to go for details about this analysis. This is a picture to show the numerical dispersion and dissipation. These are some results. And okay, fourth order scheme. Here you can try to you have more even more freedom to play with, to experiment with. I just show you here some of the possibilities. You can for fifth order scheme, you can also use different types of of constraints. But I don't think I have enough time to go through more of those details. If you are interested in, maybe we can talk later. And we can use a point value of a solution point, and also we can even use a second order value as derivative of a primitive interpolation function at this point, which gives you different schemes. Okay, this analysis, spectral analysis, dispersion, dissipation, solution. Okay. Some very preliminary understanding for this is that if we increase the point value, you can increase accuracy, but you will you will suffer a more restrictive CFL condition. If you increase the second order derivative as a constraint condition, you can largely relieve the CFL number. You can use an even larger one. Okay, this is validation of a fifth order scheme. We check the convergence rate of order. This work was actually done by Dr. Chen. This is for Euler equation. We have two tests. We show the fifth order convergence rate. These are some benchmark tests widely used in computation of gas dynamic Euler equation. Okay. So this two-dimensional one looks good. Okay. I have two slide 2 or 3 slides left. I just show you to some of the results that we apply this kind of a scheme, multi-moment finite volume scheme to environment fluid dynamics and also the geophysical, atmospheric and oceanic scheme applications. This is very widely used downbreak test to validate your code. You measure the pressure at different points, and they have an experiment. You can see if those kind of experiment can be accurately recovered by your numerical model. This is the application of tsunami, the 2004 Indian Ocean tsunami simulation. This is a kind of interaction between air and wind-driven flow and the absorption of a gas into water. Okay. Now, this is the thing most related to this program, I think. But unfortunately, I do not have enough time to go details. For a global model, okay, because of latitude, longitude grid like this, we have some trouble like this. So recently, many people shifted to this more unified spheric model, spheric grid. We have developed shallow water model for all of those grids, and they have some difficulties. But we found that over formulation, over numerical method is very easy to implement to all of those grid. So it's just some simple result of example. For a non-hydrostatic compressible model, we also very recently this work has been done by Dr. Li. To develop a non-hydrostatic model. I just pick up some of the representative results to show you it works. Unfortunately, I do not have enough time to go for more details about this part. So please join Dr. Chen's seminar next week, Monday. He will talk about this with more details. This is a summary. I use the multi-moment, and the multi-moment constraints provide a very general framework to construct conservative, simple, flexible, and efficient high-order scheme on local base. High-order scheme can be more physically compatible and intuitive. So you can feel, you can just construct things, not restrictedly follow the Gautier procedure or something like that. So things here can be more flexible, which up to now, according to our experience and our results, provide promising numeric platform for atmospheric and oceanic dynamic cores. Here are some future work. There's still many things to do to find the guidance, how to follow the guidance to get a better scheme along this direction, and more applications. So this is in some cases maybe you can include the physical stuff as a constraint in a reconstruction of a flux function. Leave some reference list here. Maybe you, if you're interested, you can check with more details. Okay. This is the picture I like very much, which is done by Dr. Yokoi, who now is working in Cardiff University, using multi-moment volume method. Okay, thank you.
Would it be possible to have the point values for velocity in a different place from the point values for pressure? To make it
I cannot answer. But I think we can. But the problem is if we need to do that. And of course, you can try, and you will have a result. So that will maybe can tell you.
Well, you said do we need to, but when you showed the modes, I can't remember the details of one of your slides, and you said that they are all very damped.
Yes.
But there was one with lambda 3 equals 0.
And
so is
this is in that case what. How to interpret this one? Yes. Maybe that means there's no calculation model mode. This case.
Okay.
Upbringing. Since I think yesterday you asked a question for this kind of dynamics talk. Theoretically, we use, for example, this is a third order equation. You will have at least 3 eigenvalues. How these eigenvalues affect your numerical solution? For this type of scheme, I believe DG is also has the same property. Maybe can partly answer your question, which is we have some computational mode there, but this mode will, as you can see, the order which is inverse of delta x in all the case. So it will disappear very quickly, will not affect your numerical solution. Only this one, which has a leading term like this is the exact solution, and the truncation error is appear here as delta x to 3 or 4 or something like that. So computational modes will definitely exist, but in some scheme they will disappear automatically So probably we do not need to care much about that.
So what about in the vertical direction? Would you need to care in the vertical direction? Would you use collocated in the vertical?
In this case, in a non-hydrostatic model recently developed by Dr. Lee, we do not use. It's still collocated, just the same as other direction.
In the vertical, you can't rely on upwinding because there's not a lot of flow. In the vertical.
Yes.
So the damping of the computational modes is not reliant on that upwinding. Is that the case?
But in this case, it's a remaining problem that we need to consider further. But in this case, we use explicit. We just use exactly the same as a horizontal, but of course we need to sacrifice the delta t, okay, whole model. There are some other options we need to explore further. For example, the explicit splitting, like a beer, maybe suggested back to 2003, 4, 2.
It goes way back.
Yeah.
So just for the spatial discretization in the vertical, you're using collocated.
Yes.
And you don't have any problem with there's no explicit damping of the
No.
And there's also there's no upwinding really in the vertical.
Yeah. There is upwinding. Yeah, exactly.
But I mean, upwinding in the vertical doesn't really help much because there's not much vertical flow.
Mm-hmm.
And it's enough. So.
But even though it was collocated, can you go back to your dispersion plots? It wasn't going to zero at the smallest wave number.
This one?
Yeah, those. Many of them were. I guess they turn down so that negative group velocity, but they're not going all the way to zero like most collocated schemes would.
You want my opinion? Or
No, I'm saying one of the reasons for staggered is to avoid the MCV3 dispersion and make it look more like MCV3 CPCC.
But this is just for a pure advection equation. I'm not sure if maybe in CFD society, at least for compressible flow computation, collocated grid is the most popular choice, and so upwinding. I believe upwinding plays a central role here to make this computational mode and automatically duct. So we do not need to care much about it. So actually, this is for conventional finite difference method or finite volume method. This curve looks like something like this. So this is pi. They dropped earlier at this stage, but here since we increase decrease freedom.
This has to be a different normalization. I think they all have to go to zero.
Yeah.
I think that's just
Yeah. We pay more here because we increase at least 1 degree freedom.
My question relates to you made an analysis of Lagrange interpolation versus Hermite interpolation.
analysis, something here. I don't think it's analysis, it's just
Yeah.
this one.
Yes. And in the Hermite interpolation, like you would also need the data about the information about the derivatives and averages, etc.
Yes,
And also in the final thing you said, like you're combining these two,
yes.
Lagrange and Hermite.
Uh-huh.
Like I'm wondering, how do you combine that?
Yeah, and this is what we do here. We calculate the solution at the collocation point. That means we calculate the point value. We update the point value. We do not update the moment, the derivative or average or integrated average. This is maybe we can call this is kind of a Lagrangian or collocation type of consideration. But for a second stage, to construct the flux function here, we use the multi-moment constraint. We do not limit ourselves to the point value where which is used in a Lagrangian interpolation.
So is it that like at the left-hand side, you use a Lagrange interpolation formula and
You mean you can even make it more flexible?
right.
I think it works. I think it works.
Okay.
Yeah. You can try. Yeah, it's interesting idea.
Okay, go on.
So in one dimensional, you use Hermite Lagrangian Chebyshev point. I was just wonder, in two-dimensional mesh, what kind of,
You mean structured grid or unstructured grid?
let's say the structured triangular mesh.
Yes, you can do that exactly as a one-dimensional.
On the, I mean, do you have points inside of the triangles or just points on the
Not triangle, rectangle.
rectangle?
Yeah.
But do you have triangular mesh? You should that.
Yes. In that case, we put the point and the values at point at the edge.
Okay, let's thank again, and we'll look forward to hearing more on Monday.
Thank you.